What's up guys, welcome to my first YouTube video. Today we're looking at trig functions and their transformations. This question comes out of the Advanced Functions Nelson textbook, so let's get started. Question 11 says, a rung on a hamster wheel with a radius of 25 centimeters is traveling at a constant speed. It makes one complete revolution in 3 seconds and the axle of the hamster wheel is 27 centimeters above the ground. Question A says, sketch the graph of the height of the rung above the ground during 2 complete revolutions, beginning when the rung is closest to the ground. So before we jump right into our sketch, let's draw a diagram of this scenario so we can identify some key points. So let's draw a circle that represents the hamster wheel. And we know that the radius of this is 25 centimeters. We also know that the axle is 27 centimeters above the ground. So we can label this distance here 27 centimeters. All right, so what are we measuring? We're measuring the height of the rung as it goes around the hamster wheel, right? And so what's the rung? The rung is just one of these little steps, right? Just like the rung of a ladder. We're just focused on one of these rungs here as it goes around the hamster wheel. From this diagram alone, we can already identify some key points, like max height. What is the max height here? Let's take a look. We have 27 centimeters, and we know that this here is the radius, which is 25 centimeters. So we know that the max height is really just 27 plus 25, which is 52 centimeters above the ground. All right, what about the minimum height right down here? We know that the axle is 27 centimeters and the radius is 25 centimeters, so we can find the difference, which is this little space here, by subtracting the two. 27 minus 25, that gives us 2 centimeters. All right, so hopefully you can start to see the diagram come together. We also know that right around the middle here, which is that axle point, we are 27 centimeters above the ground. All right, so now that we have our diagram, we can go ahead and take a look at how we can draw our sketch. Notice that we're looking to sketch during 2 complete revolutions, and the question tells us that one revolution takes 3 seconds long. All right, so let's see how we can put that together. Down here, I'll draw my graph. Let's label this height in centimeters. And down here, we can label this as time in seconds. So we know we have a height of 52 centimeters above the ground. We have a middle point at 27 centimeters above the ground. That's where the axle would be. And then we have the minimum point, which is 2 centimeters above the ground. Let's just draw the equation of axes here, just so we can kind of have a point of reference for our sketch. We're also looking to sketch over 2 cycles, which is 6 seconds, right? One cycle takes 3 seconds, so we can mark 3 seconds right around here. And we can mark another 3 seconds right around here for the second cycle. All right, the question tells us we want to draw the graph beginning when the rung is closest to the ground. This gives us a clue that we're looking to start right in the lowest position, the minimum position. So let's go ahead and try that out here. We're going to break up the graph into 4 pieces, right? Because we know that a sinusoidal graph can be broken up into 4 different pieces. And we can do the same over here as well. All right, so we start at the lowest position, 2 centimeters above the ground, right here. The rung is right down here. As it's moving, it approaches the middle height, 27 centimeters. So we can go ahead and put a dot right around there as well. Then it goes towards its maximum height, right around here, which we know is 52 centimeters. Following that, we come back down to the middle height, 27 centimeters again. And the last step of the journey, coming right back down to the starting point at 2 centimeters above the ground, we're back down here. All right, so you can kind of already start to see the sinusoidal graph taking form here. And since we know we're doing it over 2 cycles, we can just repeat the exact same pattern. Starts at the bottom, 2 centimeters, then goes to the middle, then goes to the max, back to the middle, and then finally back to the minimum point. And then we can go ahead and connect the dots again to show that we now have 2 cycles of our sinusoidal graph. And obviously this can go on forever, but we're just looking at 2 cycles here. So there's part A right there. We got our sketch of our sinusoidal graph representing this hamster wheel as it's traveling from the lowest point up to the highest point and back down to the lowest point. So we're doing it over 2 cycles. Okay, let's take a look at part B. Part B says, describe the transformations necessary to transform y equals cosine x into the function we graphed in part A. And actually, let's look at part C as well. Write the equation that models this situation. So we can kind of actually look at these two at the same time. I'm actually more inclined to do part C first, since that's going to be a little bit easier. We know that we're trying to base this off a cosine graph. And we know that a cosine graph can be represented with this general equation right here. Right? So let's go and find each of these components. The A, K, D if there's any, and then the C as well. Well, because we've already drawn the graph, we can easily identify each of these components. The A is just the amplitude, which is just how far from the middle line do you travel up to the maximum, or how far from the middle line, your equation of axes, do you travel down to the minimum. If we go back to our diagram, you'll notice that the A value, or the amplitude, is actually just 25 centimeters. That's going to be the radius of this hamster wheel. So already we can put together the equation 25 cosine. Now the K value. How do we figure out this K value? The K value is dependent on the period, right? There's a formula that you would have learned where the K value is equal to 2 pi divided by the period. Well, the period in our case is 3 seconds, right? Because it takes 3 seconds to complete 1 cycle. So take a look at this. This is our K value right here. Pretty easy. 2 pi over 3. All right, let's take a look at this D value, which is the phase shift at the end, since that's going to be the harder one. Next is the C value. That's just the equation of axes, right? If you look at our diagram and our graph, we can see clearly that our equation of axes is just this middle line right here, right? It's the average between the maximum height and the minimum height, which we know to be 27 centimeters off the ground. And 27 centimeters off the ground represents that axle length from the question. So pretty easily, we can say that the C value here is 27. All right, so let's get back to the D value now, the phase shift. How can we determine what the phase shift can be if there's even a phase shift to begin with? Well, pay attention to this graph right here that we drew from part A. We actually have a graph that looks pretty similar to a cosine graph, right? So let's take a look at how a regular cosine graph would look like on our set of axes right here. Cosine starts at the maximum, then goes to the middle, then the minimum, back to the middle, and then back to the maximum. There's 1 cycle of cosine right there, so I'll just draw that so you can see. Right? And we know, because we're doing it over 2 cycles, we can repeat the same pattern. Maximum to the middle, middle to the minimum, minimum to the middle, and then finally back up to the maximum, so we can draw the 2nd cycle of cosine here. Our graph, the blue graph, is actually just a reflection of this. Right? If you can imagine the cosine version of this graph just being reflected, it would overlap exactly on top of this blue graph right here. Right? And there wouldn't be any phase shift that's needed, because at that point then, the graph starts exactly where a negative cosine graph would look like, right at the minimum. So all we need to do then is to tack on a negative in front of our a value and eliminate the need for any d value. So what would that give us right here? That would give us y is equal to negative 25 cosine 2 pi over 3 x plus 27. All right, so this would be our final equation. All right, let's look at part B, where we are asked to identify all the transformations that we need to go from the base cosine graph to our transformed graph over here. So let's read them left to right and describe all the transformations. That negative sign over there indicates that we would have a reflection in the x-axis. The 25 would be an indication of a vertical stretch by a factor of 25. The k value indicates horizontal stretch or compression. So if you want to know which one you would correctly pick, you would look at the 1 over k value to see what that outputs. So if we do 1 over 2 pi over 3, we know that that's just basically a division of fractions. So we can take 1, the numerator, and actually multiply it by the reciprocal of the denominator. So if we assess this, we just get 1 times 3 over 2 pi, which, if you want to just convert that to a decimal number so you can understand what that looks like, is just 0.477 approximately, right? Because it's less than 1, this indicates that we actually have a horizontal compression by a factor of whatever this value would be, 3 over 2 pi exactly. And lastly, we have a vertical shift, or vertical translation rather, same thing, up by 27 units. All right, and there you have it, part B, all the transformations that you would need to go from a base cosine graph to our transformed graph over here. All right, guys, that's a wrap. Thumbs up if you found this video helpful, subscribe if you want to see more like this, and comment down below what chapters you might be struggling with, and I'll put up more videos just like that.